Hello everyone. Today we decided to make a webinar about vibration test theory, and this particular webinar we're going to talk about sine test theory and its basics. Naturally, the majority of our attendees know the theory, but it never hurts to brush it, especially if you are doing installations, trainings for new users. In this webinar, we will explain the basic principles of vibration controller and sine test, and we will show how RULA controllers simplify all the process by making all these calculations automatically. And before we start, let's talk a little bit about the contents. Today, I'll make the definition of the control. We will talk about the control theory. I'll describe two main types of control. After that, we'll go to the sine test theory. We'll talk about the signal generation, uh, the process of collecting response from the system, and we will talk about the voltage regulation. And we're hoping to make this webinar interesting and worthwhile. Now, let's start with the basics. In engineering and mathematics, control theory deals with the behavior of dynamical systems. And the main definition in control theory is called control. As you see on the slide, control is such an impact on an object which allows us to reach desired values or parameters of some kind of an object. In control theory, we have two ways of control, and the first one is called open loop. In open loop control, we don't take output signal, which is shown here by Y, into account. As an example, we can take a regular generator. We only set the output signal parameters and don't control the output values and voltage. Another way of control is called closed loop or feedback system. Here you see it on the slide. In feedback, we get the resulting output from our object and use it for regulation. Here you see that we have some kind of an output from our object and it goes into our controller. Here you see the main scheme of the controller. On the left side, it's the most basic and common one. Here we have our task input, controller output signal, and object's output signal. In this example, we calculate the difference between our task input and response from our object. After that, we sum up it with our output signal, and in that case, we regulate our object's output. Sometimes it takes several iterations to get a desired task. But to decrease the number of regulations, you can change your subtraction with division and addition with multiplication, like shown here. In that case, we will get less iterations of the control. And now let's talk a little bit about compression. Sometimes we can add coefficient value to our system, and it's called compression. This value is used in nonlinear systems with noise, and it helps during the regulation. Using this coefficient, we set the minimum and the maximum regulating values for our system, and basically the compression is the ratio of input signal to feedback. And here on the next slide, you see the graph. The blue line is our desired task, and we have red and green line. The red line is the system output without compression. You see that on the second iteration, we get a really high level and the regulation isn't smooth. But using compression with this green line, you see that we are really close to the task and it takes less regulations to get the desired value. And now I think we are done with the control theory, its basics, and now we can go to the sine theory. Let's divide it into three steps: the generation process, getting the response, and the output voltage regulation. Here we have our basic controller scheme, and every time we go to the next point of our content, you'll see that one of its parts, which is connected with this topic, will be green. Our first step is to generate sine. Here on the right side, you see that we generate our signal in this point of our scheme. And basically, to generate sine, we use the basic formula. Here you see it. To generate the if fixed sine with the frequency f and sample rate fs, we use this formula. And I need to mention that every time this coefficient overlaps a whole value, our sine goes through the 0 point here. You see it with red dots every time we overlap a whole value. I think that the sine generation is the easiest part of this theory, and I think we can go. If a lot of users asked about sine amplitude calculation, and I need to say that in our software we have an ability to recalculate acceleration into velocity and displacement. Here you see all the formulas. I think you are familiar with them. And now I can show you that in our software, we have an ability to set up the profile with all these features. Here you see we have some kind of a profile, and here we have our amplitude. In this combo box, we can set displacement, velocity, or acceleration. All these recalculations are made automatically, so you can set the profile in the units you need. I think it's a very useful feature, and also we have some kind of calculators for sine. Here we have a special calculator which calculates frequency, acceleration, velocity, or displacement by two other values. For example, I enter frequency and acceleration, and as a result, I get velocity and displacement. Now let's continue with our main topic. And the second part of sine theory is collecting data. There are four ways of collecting the response data. The main one is RMS and Synchronous Detector, and we have two additional ones, peak and mean. Let's start with RMS. I think this formula is really basic. Here we have the resulting RMS value. To calculate this, we need to sum all the samples and divide it by the number of samples. After that, we get the square root, and it's our required RMS value. I think it's the most simple way, but sometimes we can receive errors. To make calculations better, we use Synchronous Detector. When you have a noisy system or you have 50 Hertz from the socket, you can receive some errors. You need to use Synchronous Detector. This method is based on translation the current frequency into the zero, and after that we find its mean value. To calculate data using Synchronous Detector, we need to calculate the sum of sines and cosines. Here you see these two formulas, and I need to say in this method we can use window functions, but it's optional. Here you see that we multiply our sum of sines and cosines on window function. But sometimes this method has disadvantages, like shown here. You see that we have a sine signal with an amplitude of 5, but it has a fractional number of periods during the regulation time. And in that case, we will receive 5.14 amplitude value using synchronous detector without windows. In that case, we use window overlapping. Here you see we place a window function on our sine, and we reduce our error. But after using the window function, we can lose some data shown here in yellow. To do this, we overlap windows like shown here. Blue, black, and red are windows here. And to calculate the resulting synchronous detector, we calculate the real and imaginary part of our amplitude. We multiply sine sum with the cosine sum and multiply them on coefficients. And C here is a normalized coefficient. Here you see we need to sum all the window function samples, divide them by the number of samples, and invert this coefficient. As a result, we get this formula and calculate the resulting amplitude. So let me show you an example. Here we have a noisy sine with the frequency 122 Hertz, and the 20% from its amplitude is noise. We know that the task amplitude is 5, and let's make some calculations, and using error mask method, we receive the resulting amplitude as 5.19 and get 3.8% error. But you see that using synchronous detector, we get 4.995 amplitude, and the error is less than 1%. And you see that when you have some noise on your signal, it's better to use synchronous detector. Do we have any questions?
Let me just check the question box in a sec. Yeah, here is a question about the window functions. Which window function is used?
In our software, we use hand window. I think this window is really good for sine, and we get really nice results using this window. We tested other, but this one is better.
Han, yeah?
Yeah.
Okay.
And the two other methods of collecting data are called peak and mean. They were added into our software for our customer. And the first one is really easy. We get the minimum and the maximum value by on one channel and divide them by 2. And using mean method, we sum up all the samples and divide them by the number of samples. And these two methods are really easy, but there may be some situations when you need to use these options of collecting data. And now let's go to our software. Here in the channels tab on the profile, you see that you can select the algorithm of the calculation. Also, in our sine test, we can set multiple channels as control, but as you heard previously, we can have only one response channel. So in that case, we need to select the control strategy for our setup. We can have 3 different options. The first one is when we select the channel with the maximum value. The second one when we select the channel with the minimum value, and the third one we enter the weight coefficients, and in that case all the response is multiplied by these coefficients, and after that all the control channels are summed up. So I think in some ways you can change it and use the algorithm which is better for your situation. And now we really need our part which is called regulation. Here you see that the regulation happens in this part of our controller. And basically, in this part, we calculate an error using this formula. But you see that in some kinds, and you may know that it's better to calculate the exponential error and get smoother results. Here you see the graph exponential error versus regular error, and you see that it's better to get exponential error in some ways. And as it was said previously, you'll receive scripts, and there you'll see the main advantage of exponential error to regular error. And here we see our graph. The blue line is the task here, and the red line is our response with regular error calculation here. And you see that it's not really smooth. But when we have exponential error, the green line, you see that we are really close to the task. I think now we covered all the principles, all the main principles of the control theory. We discussed the main formulas of sine signal generation. I covered all the types of collecting system response, recalculating it, and showed you the main options for our software.
Yeah, we hope that after this webinar, some basic formulas and some principles of the work of our vibration controllers have become clearer to you. However, we understand that maybe this is the kind of information that you need to have in a visual form. So we'd be happy to send you the presentation and the backup materials for you, for your colleagues and your prospective clients. So in the follow-up emails, we will either send them or maybe we will offer them, like depending on whether you think it's useful or not. And we will really appreciate your feedback on this, experimental format, more theoretical format. And now it's time for your questions. So we have a little time. Are the principles and formulas the same for different test types like random?
The control theory is the base for our tests, but regulation and generation is different for our tests. For example, in random test, we regulate frequency response, not the amplitude. And I think we have another question about the compression. The compression is a coefficient, and here in our software, we set it really strictly. Here, the control is the main tab for the settings. And here on the left side, you see that we set compression rate here. You see there is some help for these settings. And in the follow-up and the scripts, you'll see the comments in the code and see that compression is really important here.
So when you open the software, is it default? So do you have the default value of compression?
I need to say that when I run all the tests, I don't change the settings, and I think that these default settings are really nice. and you don't need to change these coefficients. I like them.
So yeah, I guess you really need to understand these formulas and to understand the idea of the control theory very well in order to alter the compression when it's necessary.
But about the compression, sometimes you need to change them when you need to change the regulation process. For example, increase the startup time, or if you don't have a really strict control.
Can a controller work as open loop?
Yes, in our software we have this option, but it's placed here in diagnostics window. Here we have our oscilloscope. On the right side, we can set the voltage and the frequency. And we use this window only for diagnostic checks.
Like pre-start check, yeah?
Yeah, we don't run our controller as an open loop and don't recommend you to do it with your control systems.
For random spectrum, can I recalculate between velocity displacement and acceleration using the harmonic vibration formulas? Can we answer that now?
Yeah, we can answer this question. Let's go to our presentation here. Here you see these formulas, and for random test, you can recalculate acceleration, velocity, and displacement using these formulas, but this recalculation must be done for every frequency, and the values must be squared. In that case, you'll receive your measurement unit, but you can do this for random.
All right, I guess that's all for now. If you have any questions left, please don't hesitate to send them in the follow-up, and we will also answer each question in the follow-up. So if you ask that, we will just make sure that the answer is in the follow-up email, so you don't miss the information, because sometimes it's difficult when you can just hear it, right?
And I think we have a question about the scripts. For understanding all the process of recalculation, I'll make a small guide how to use these scripts and what all these formulas mean. And so you won't get any troubles.
Yeah, we really hope that this webinar was useful for you. And we hope to see you in our next events. I guess this year we'll have just one webinar just before Christmas, and that's it. And if you have any suggestions for the topic, which is really urgent and necessary for you, you can type them now or later in the answers to the follow-up emails. We really welcome your feedback and your suggestions. And for now, thank you so much for joining us today. Enjoy the rest of your day. And if you have any connection to American culture, happy Thanksgiving.